So yesterday we got as far as talking about moving air in and out of the alveoli, and we closed with the idea of compliance and elastic recoil. And what we have up here at the beginning is simply a formalization of that. It's a mathematical equation saying that compliance is equal to the change in volume divided by the change in pressure. If we were to look at this as elastic recoil, it would be the change of pressure over the change in volume. Now, I think the easiest way to think about compliance is with balloons, and I'll start sort of a discussion of that when we begin the lecture. Now, the next thing we want to spend our time on today, though, is alveolar gas exchange. After all, we've described the oxygen moving across those exquisitely thin epithelia and endothelia in the alveolar space. And what we want to talk about now, though, is how this gas exchange functions. Now, I'm going to give you this long-winded definition and all, but when you come to the end of it, this Dalton's law of partial pressures is simply a means of talking about concentration of gases. Now, the formalization of this statement is that Dalton's law of partial pressures holds that the total pressure of a gas is the sum of the partial pressures of the gases in the mixture. Now, if we look at the air around us, we find that something like 79% of the air around us is nitrogen, and about 21% is oxygen. So that means that 21% of all the air is oxygen, 79% is nitrogen. So if you take 0.21 times the atmospheric pressure, which we're going to see at sea level, is 760 millimeters of mercury, that will give you the partial pressure for oxygen. You can do the same thing for nitrogen. You can do the same thing for carbon dioxide, but carbon dioxide is down around 0.04% in the atmosphere. So we'll walk our way through that, and there'll be a couple of ideas to come out of it. First is this Dalton's law of partial pressures, but then what we want to think about is how the pressures change with altitude. Now, wherever we go on the planet, whether we're on the top of Mount Everest, even if we're up at, 20 kilometers, then the relative percentages of gases are the same. It is no matter where we look, we have 21% oxygen, 79% nitrogen. What changes as we go up in altitude is the pressure. So that what we're thinking about here, and these are arcane terms, and they're hardly used in any other place other than in biology. And these are millimeters of mercury. And the millimeters of mercury term simply says that if you're standing on the beach in New Jersey and you have a J tube or a U tube of mercury, where one end of that tube has been evacuated, is in a vacuum, and the other is open to the air, that the air pressure, the molecules, the mass of air molecules above you at the seashore will raise that column of mercury 760 millimeters, 3/4 of a meter. But as we go up in altitude, there's ever less atmosphere above us. So we have less and less mass of atmosphere above us. So as we go up in altitude, the generation of the force at a given temperature will be less and less. So if we take the measurement of how high the column of air can push a column of mercury as you're sitting in your seat here, it's about 630 millimeters. If we go up to 10,000 feet, which around here is just about tree line, a little below, then we're at 523 millimeters, and that's of both oxygen and nitrogen. If we go up to Mount Everest, we're down around 253 millimeters of mercury. Just to point out that the higher we go, if you put your phone away to appreciate it, that the higher we go, the less air we have above us and the less pressure. These really are important parts of the lecture, and I think you should listen rather than being on your phone. Okay, so what we're going to do is we're going to talk about the change in pressure as we go up in altitude. And then we're going to talk about this idea of Henry's law, where Henry's law says that gases go into solution in water in proportion to their partial pressures. So as gases go into solution in proportion to the partial pressures, and I'll tell this story in terms of what we have basically in a can of beer, and the idea of CO2 reaching its equilibrium, because CO2 will be in solution in a can of beer. And then we'll spend a little bit of time describing how this becomes important. Henry's law becomes important because the gases will go into solution in a very thin water layer sitting immediately over the apical surfaces of the epithelial cells. Remember, we have to move the gas through those epithelial cells, through the endothelial cells, and into the blood. And so the idea of Henry's law is important because we have to get these gases to go into solution, to go across the epithelium and get into the blood. So then what we have to think about, though, is what's going on with the partial pressures down in the alveolus. It's one thing to think about the partial pressures in the atmosphere around us, but after all, the business end of the respiratory system is down here in gas exchange with the alveolus. And we find that when we work our way through the concentrations in terms of percentages or partial pressures of these gases down in the lung, what we find is that rather than being, 21% of the concentration of the air being oxygen, we're now closer down to 14%. And what we also find, because of all of this water layer over the top of the epithelial cells, the water concentration is down around 6.5%. So it's making a significant contribution. This is basically in this confined space, it's 100% relative humidity. Then the other major player in here is carbon dioxide. I want to spend a moment on this because this number, carbon dioxide down in the alveolus at over 5%, is remarkably high compared to the world around us. The air around us just now is around 400 parts per million carbon dioxide. We just passed that level. And that is rising, and we're concerned about that for global climate change. But down in the lung, we have over 100 times more carbon dioxide than we have in the air around us. And this high concentrations of carbon dioxide, which are a result of the carbon dioxide generated by oxidative phosphorylation and the mitochondria out in the tissues, this high concentration of carbon dioxide now is going to have implications for how we affect the hemoglobin and how we get rid of the carbon dioxide across the epithelium, the alveolar space. And we'll talk about that in quite some detail. And finally, I want to talk a little bit about the oxygen dissociation curve. After all, this story of close to 14% oxygen in the alveolar space is all about moving the oxygen across the epithelial cell, the endothelial cell, and into the blood. And what we're trying to do here is we're trying to get the oxygen to load onto the hemoglobin and the erythrocytes. We've talked a number of times about how the erythrocytes are whirling by the alveolar space, and in a matter of a fraction of a second, we fully saturate the hemoglobin. But what we have to think about here is the relationship of the oxygen concentration to the number of hemoglobin molecules which contain the oxygen. What we're going to see here is we're going to lay this out as a dissociation curve, and what we're going to do is we're going to plot the percent saturation on the ordinate, and we're going to plot the millimeters of mercury of oxygen on the axis. And we'll see, once we get up around 100 millimeters of mercury, that hemoglobin is fully saturated. But we'll see that when we draw these curves, it's not a straight curve. It's a sigmoid curve. And as a sigmoid curve, we'll see that this tells us that there's cooperative binding. There's the binding of the first oxygen molecule to hemoglobin is a fairly low probability event. But the binding of the first increases the probability of the binding of the second, the third, and so forth, until we saturate the binding of all 4 ions on those hemoglobin molecules. And we'll walk our way through that curve. So what we want to start with, though, let me just tell you the story to try to give you a sense of what we mean by compliance and elastic recoil. And sometimes, to me, this sort of sense of compliance, elastic recoil, when you're talking about the lungs, gets a little bit arcane. But it becomes more real world if you imagine that you're going to hold a birthday party and you go out and buy some balloons. And you go to the grocery store and you pick up those really cheap balloons and you stretch them a little bit, you put them up to your mouth and you blow them up. They're easy to blow up. So a balloon that's easily blown up has high compliance. But now imagine you want to make those fancy sculptures, the balloon sculptures, that people make all these fabulous shapes out of. You know, on those, what you have to do, if you take one of those balloons and you bring it up to your mouth and you try to blow it up simply by using the strength of your intercostal muscles and exhaling. So you start to blow this thing up and you increase the pressure and you increase the pressure and you think you're going to have a stroke because it just won't expand. And that means there's tremendous elastic recoil. If you can get the air into that balloon and you let it go, it collapses really fast. So that's an example of elastic recoil, and you probably better get a pump to blow those balloons up. But that shows you the difference between the compliance, where they are easy to blow up and deflate easily, whereas with high elastic recoil, they're very difficult to inflate and they deflate very rapidly. And you can apply those very same ideas in thinking about the diseases we talked about yesterday with the high compliance disease of emphysema and the high elastic recoil diseases of fibrotic disease, basically accumulation of protein in the extracellular space. But what I want to do now is I want to think about alveolar gas exchange. And alveolar gas exchange begins with Dalton's law. And early in the 19th century, Dalton said that the total pressure of a gas is the sum of the partial pressures of the gases in the mixture. Now we're going to start a discussion here of millimeters of mercury, and we're going to start a discussion of pressures of these gases. But in fact, when you look at this, think that these pressures are simply another version of concentration. And in fact, it's no surprise that this guy Dalton, who developed the idea of Dalton's law of partial pressures, is the same guy who developed the ideas of molarity and concentration. It's the same source of thinking. And what we're going to do here, though, rather than talking about millimoles and moles, is we're going to use a different form of concentration, and that different form of concentration is going to be in terms of millimeters of mercury. Now, millimeters of mercury arises from the early experiments, and some of these experiments were done all the way back in the time of Boyle, in the early, and that was during the 17th century, where what they did is they took a column of mercury, where this is mercury, and in this end of the tube, they sealed this end of the tube and they generated a vacuum. So basically, there's no air up here. So then they asked the question, if we take this so-called U-tube, that's U, not like the modern one, the U-tube, and ask the question, how high does the air pressure, raise this column of mercury? And by doing this over and over again at certain temperatures, standard pressures, they said at sea level, the mass of air above this particular certain square centimeter of mercury would raise this column of mercury to 760 millimeters. So that's the pressure. But in fact, when we think about air, and if you talk to an atmospheric scientist, they'll tell you about the argon and all of that. We're not going to worry about it. What we're going to say is air is composed of 79% nitrogen and 21% oxygen. So then from Dalton's law of partial pressures, which says that the total pressure is simply the sum of the partial pressures, we can then estimate what proportion of the 760 millimeters is contributed by the oxygen and what proportion of the 760 millimeters is contributed by the nitrogen. And when we do this, we take 0.79 times 760, and we take 0.21 times 760. This is about 160. I think that's right. And then this is going to be about 600. Is that right? I hate doing math in front of people. 0, 6, 7, 0, 12, 15, 0, 6, 9, 5, 1. Yeah, there it is, 159.6, 160, close enough. And so that then tells us that the law of partial pressures is saying that 21% of the pressure, or 160 millimeters, is from oxygen, and the remainder is from nitrogen. We can run these same numbers, and I'll let you do that, but of course, since we are at altitude here, we're over 5,000 feet, then we have a smaller column of air above us going out into outer space, so there's less mass of that air above us. And so that means the distance through which the mercury can be pushed is less. And so if you do the numbers here in Fort Collins, in the room where you are now, we still have 79% nitrogen and 21% oxygen, but the atmospheric pressure is in the neighborhood of about 630 millimeters of mercury. And it's fairly linear, so that by the time you go up to 10,000 feet, you can certainly do this, or if you go up to Trail Ridge Road around here, you're well over 11,000 feet and you're above tree line. And these numbers then are going to fall down to around 520 millimeters of mercury. And all of this will be important, because as we work through this, we're going to find that the partial pressures of oxygen are going to determine how much oxygen our hemoglobin can carry. So the higher we go, the less ability we have of our hemoglobin to carry oxygen. And in fact, if you talk to people in the Air Force, once pilots get above about 10,000 feet, they want the pilots to put on oxygen masks because they're down far enough, and what we'll see is the oxygen cessation curve is they worry that they may not be fully saturating their hemoglobin. And if you're operating a $100 million airplane, they want your hemoglobin to be fully saturated. Well, we can go through all of those calculations. I'll let you do the numbers on top of Mount Everest and so forth. But what we want to think about, though, is what's going on down in the alveolar space. Because this is true for the air around us, but that doesn't tell us the whole story of gas exchange in the alveolar space. And you remember from what we've talked about the last couple of days, the business end of the respiratory tract is down here, where the epithelial cells, the alveolar epithelial cells, meet the underlying endothelial cells of the pulmonary capillaries. Because after all, what we're trying to do is we're trying to load these erythrocytes with oxygen. Now I'm going to give these numbers here as percentages, but you can really simply think about them as concentrations, and it works just fine to talk about these things as concentrations. And when we talk about the alveolar space, down here we find that the nitrogen is in the neighborhood of about 0.749, but 74.9%. When we talk about the oxygen, though, we're now in terms of about 0.137, more or less 14%. Now, this is about 6% less than we saw in the air. Part of this is because we're down deep in the lung, and we now have to move air in and out to get the oxygen concentrations down here. So we have some gas exchange, and some of it has to do with the fact that we have the composition of air down here also contains water. And water is in the neighborhood of about 0.65. 0.065, 6.5%. And carbon dioxide is in the neighborhood of about 0.052. It's about 5%. So a considerable amount of gas down here in the alveolar space is carbon dioxide. And that's in contrast to the world around us. Because if you think about atmospheric carbon dioxide is about 400 parts per million. 400 parts per million works out to be 0.04%. And yet we're down here at 5%. So we have over 100 times more carbon dioxide down in the alveolar space than we have in the outside world. So there's an enormous amount of carbon dioxide here compared to the outside world. And we're going to use this carbon dioxide metabolically in a number of ways, and we're going to talk about how it comes to equilibrium. Well, if you work your way through this and work this 0.052 at standard temperature and pressure, so you do 0.05 times 760, you come out with a number here that's in the neighborhood of about 40 millimeters of mercury. If you work your way through this number for the oxygen, you come out with a number of 0.14 times 760. You come out with a number in the neighborhood of about 106 millimeters of mercury. So those effectively are the concentrations of carbon dioxide and oxygen down here in the space of the lung, the alveolar space. And what we're trying to do, the functional significance of this, is we're trying to move oxygen from the alveolar space, the air, across the epithelium, across the endothelium, and into the hemoglobin on the erythrocytes. If we look at the concentration of oxygen coming back from the tissue, so we're going to have the flow in this direction. So this is going to be the partial pressure, the PO2, of oxygen in blood returning from the tissues. This number, if you translate it out of percentages and bring it back to millimeters of mercury, this number is about 45 millimeters of mercury. If we look at, I'm sorry. This is down around 40 millimeters of mercury for PO2, but if we use PCO2, the partial pressure of PCO2, this is in the neighborhood of about 45 millimeters of mercury. So, like this? Yes. So now look what we've done. To give these numbers, we have 45 millimeters of mercury as the partial pressure of CO2. And we have 40 millimeters of mercury as the partial pressure of oxygen. Now, let's take it away from these arcane terms of millimeters of mercury and just think about where things are in higher and lower concentration. The number here for oxygen is 106 millimeters of mercury in the alveolar space. That's roughly 2.5 times as great as the concentration of oxygen returning from the right side of the heart returning from the systemic vasculature. This is the partial pressure of oxygen out in the tissues. So that's telling us this is 106, and this is 40. You can think of this as concentration gradient. There's 2.5 times as much here as here. So now oxygen is simply going to want to move down its concentration gradient. There's simply going to be the random walk that we've seen so many times before. But put your phone away, I'd appreciate it. The random walk has to do with the movement of ions, in the most part we talked about in the past. But now we have a random walk of gas molecules. But it's the same story. Things move from regions of higher concentration to regions of lower concentration. So in this particular case, the oxygen is diffusing from the alveolar space across this very narrow epithelial cell, a narrow extracellular space, narrow endothelial cell, and into the blood, where it can then bind to the hemoglobin. Because remember, we have these hemoglobin molecules with their iron atoms having a high affinity for oxygen. So oxygen is going to be taken on here. Now similarly, and we're going to just leave this as partial pressures, and then we'll spend more time on carbon dioxide later, but we have the same story for carbon dioxide, where the carbon dioxide concentration in the blood can be thought of as 45 millimeters of mercury. That's 5 millimeters of mercury higher than the concentration of carbon dioxide here in the alveolar space, because this works out, as we said, to 40 millimeters of mercury. That's a long-winded way of saying this. We have the appropriate concentration gradients. We have gradients that are going to allow for carbon dioxide to move from the blood vascular compartment into the alveolar space, and concentration gradients allowing for oxygen to move from the alveolar space into the blood vascular compartment. It's simply this concentration gradient described here in terms of millimeters of mercury. That's all we're doing. And oxygen is going to move into the blood vascular compartment, and carbon dioxide is going to leave. So any questions to there? Yes?
How much does it change? So like when you're doing oxygen care, like when you make a cannulation, like saturated with oxygen, or you do like a whole mask that like.
So the question here is, what happens when you're taking on oxygen? Hold on to that question. I think that question is better approached when we look at the oxygen dissociation curve. And what we're basically going to see is, if things are healthy, it doesn't much matter. Because at 100 millimeters of mercury, you're going to fully saturate the hemoglobin. But when you start to take on oxygen is when there's something wrong with the exchange here. There's something wrong with the heart. There's something wrong. For some reason, we're not getting appropriate exchange. So we up the oxygen concentration here, trying to increase the gradient. But we'll see that under normal circumstances, you saturate just fine. It makes sort of a joke of the oxygen bars. Anything else? Yes?
I think you might have mentioned this earlier, but like the higher concentration of carbon dioxide in the atmosphere, does that mean there's too much coming in from the lungs, and that it's messing up like how the...
Oh no, okay. So the main idea I wanted to say about the carbon dioxide, we can come back to here. The carbon dioxide is about 0.04%. So that's 0.0004 times 760. That will give you the millimeters of mercury of carbon dioxide. You're going to see that's a pretty small number. But down in the lung, because we have so much carbon dioxide generated in the tissues, and we're basically moving the carbon dioxide back to the lung to expel it, to get rid of it. Under those circumstances, the partial pressure of PCO2, partial pressures, is in the neighborhood of about 5.2%. I do it this way. It's about 5%, so it's 0.052. Take that times 760, and you come up with a number that's in the neighborhood of around 40 millimeters of mercury. Again, these are big numbers compared to this number. And so we simply have way more carbon dioxide in the lung than you see in the outside world.
Oh, I meant like with the depletion of the ozone.
Oh, you're okay. So as far as changes in carbon dioxide levels that we're seeing because of fossil fuel burning, that has almost no effect on our breathing. That's a longer term effect on capturing heat and holding heat in the atmosphere. Turns out that carbon dioxide, when sunlight comes through, the carbon dioxide provides a kind of insulating layer. And so we effectively are making a greater and greater insulation layer around the planet. So we tend to radiate less heat back off into space. So there's a slow buildup of heat within the planet. Right now, much of that heat, much of the carbon dioxide is being taken up by the ocean. Only time, but that will end eventually. Does that answer your question?
Yeah.
Okay. Anything else? Okay. So now, the next thing I want to think about and is that, remember, we said yesterday that all of these epithelials are covered with a thin layer of water. And we said that we had to be careful not to get this layer of water too thick because that would increase the diffusion distances, and that was pneumonia. But under normal circumstances, there is a very thin layer of water, no more than a couple of micrometers at most, of water over the surface of these epithelial cells. But because this is a confined or closed space with that thin layer of water, the gaseous water's basically evaporating and condensing back into this water layer. That means we have 100% relative humidity in this space. And that tells us about 6% of the gas molecules in the alveolar space are water molecules. That brings us round to this idea of the importance of the water layer, and that brings us round to the concept of Henry's law. Henry's law says that gases go into solution in water in proportion to their partial pressures. To give you some sense of this, I want to give you a sort of a real-world example. So let's imagine we have a can of beer. Could be a can of pop. Could be a can of soda. And we have a top on it. Now, you know that a beer or soda has carbon dioxide dissolved in fluid, basically in water. If you would measure the carbon dioxide level in this closed container, you'd find that almost all of the gas up here is going to be carbon dioxide. This is going to be almost entirely CO2. So we can think about this as more or less 100%. Now, once we open the can, or if you pour the can into a glass, you'll notice the bubbles coming out. The bubbles that are coming out are carbon dioxide. And the carbon dioxide, which is coming out of the fluid, is related to Henry's law. Because here at 100% carbon dioxide, we've put as much, we're at equilibrium. So basically, the partial pressure of PCO2 is probably close to over 760 millimeters of mercury. So that's all CO2, and it's at equilibrium. But we know what happens if we open a can of soda or a can of beer and let it sit any period of time. It goes flat. And the reason your beer goes flat is Henry's law. Henry's law is simply saying that the partial pressure, the PCO2 in air, is in the neighborhood of that number up there. So it's a fraction of a millimeter of mercury. So that means the this carbon dioxide comes out of solution and goes into solution in the air, and the number of molecules of carbon dioxide available to go back into solution in your beer is practically nil. So this is another way of exemplifying Henry's law. Simply says that gases go into solution in proportion to their partial pressures. In a closed can, the partial pressures are really high, probably 100% CO2. But when you open it, now the partial pressure of CO2 is practically nothing, and that allows the carbon dioxide to leave. But Henry's law becomes important here. We need to be able to put all of these gases, but especially oxygen and carbon dioxide, in solution in the water layer so they can diffuse down their concentration gradients from the alveolar space and into the blood capillary. So far, what we have described here is simply the movement of oxygen from region of higher concentration to region of lower concentration. Yesterday, we emphasized that the dwell time, the period of time when these erythrocytes are close enough to the alveolar space to take on oxygen, is a fraction of a second. Even as you're sitting there quietly, it's probably 3/4 of a second. When your heart rate goes up around 150, 180, then the dwell times here are down around 0.25 to 0.3 seconds. But even at those short dwell times, less than 300 milliseconds, the oxygen diffuses down its concentration gradient and fully saturates all the hemoglobin molecules in the erythrocyte. So that's where we want to go now, is thinking about the saturation of these hemoglobin molecules from the oxygen diffusing down its concentration gradient. We do that by, and we show this, we describe this by drawing something known as the oxygen dissociation / association curve. So what I'm going to put on the board here is the so-called oxygen association curve. And we're simply going to plot oxygen concentration in millimeters of mercury versus percent saturation of hemoglobin. So on the axis, we're going to plot PO2s, partial pressure of oxygen. And on the ordinate, we're going to plot percent saturation of hemoglobin. Now, as we plot this, we get this really interesting curve. It's kind of flat at the bottom. As we increase the partial pressure of oxygen, it shows this sigmoid shape. So this is a sigmoid shape. It's a sigmoid-shaped curve, suggesting cooperative binding of oxygen, hemoglobin. Now, if you get down to the nuts and bolts of this, you can do this kind of plot for any number of molecules. You can look at this in pharmacology, and you can look at this in enzymology. And you end up with a slope here. And the slope tells you the number of binding sites. And this slope with the number of binding sites has a name in physical chemistry and pharmacology. It's called a Hill coefficient. When you look at the slope of this curve of percent saturation versus partial pressures of oxygen, you find the Hill coefficient is 4. This tells us that there are 4 binding sites. For oxygen. It's no coincidence that the 4 binding sites of oxygen is the same as those 4 iron atoms in the hemoglobin molecule. What we're looking at here is the probability of binding an oxygen atom to the iron atom in hemoglobin. And as we increase the concentration of oxygen, we change the probability of binding to the hemoglobin. And fundamentally, we can see here that we bind the first site, and then we bind the second site, and the third site, and the fourth site. And here in the steep part of the curve, we find that when we're binding the number 3 site, if we follow this over, this is about 75% saturated. If we follow this number down, the partial pressure where 3 of the 4 sites are bound, where we have 75% saturation, that number down here is the neighborhood of about 40 millimeters of mercury. You'll notice that those are the numbers we used in the upper panel, that we said that the concentration of oxygen in the blood returning from the tissues is about 40 millimeters of mercury. When you draw this so-called oxygen association dissociation curve, when you draw this curve, you find that this is telling us that when the hemoglobin is returning to the lungs after it's made its circuit through the systemic vasculature, 3 of its 4 sites are still bound. So we've only given up about 25% of the oxygen from the hemoglobin. Now, if you were to take the same measurement of blood coming through the myocardium of the heart, returning to the right side of the heart from the myocardium of the heart, then you would have extracted more like 80% of it. But here, for the blood coming back to the systemic vasculature, 3 of the 4 oxygen molecules are, 3 of the 4 iron atoms are still occupied by oxygen. This also becomes important because remember, in that upper panel, we're saying we have a very short period of time to bring the oxygen back onto the hemoglobin. So because we're up in the upper reaches and the steeper part of the curve, we have a pretty good opportunity of binding that 4th oxygen to saturate the oxygen. I'm sorry, to saturate the hemoglobin. Couple of things from this. First, this sigmoid curve is telling us that the probability of the first oxygen binding is reasonably low. But once we bind the first, we improve the probability of the second, the third, and the third, the fourth. And this brings us back around to the idea that because we're on such a steep part of the curve, during that brief period of those erythrocytes whirling by the alveolar space, we can recharge those hemoglobin molecules fully with oxygen. The other point, this speaks to the question that came up earlier. If we come out here, if we go up a little bit farther in the curve, and we find that we are 100% saturated, and we work our way over to this side of the curve, we come down here at 100% saturation at a point which is more or less about 104 to 106 millimeters of mercury. So 104 to 106 millimeters of mercury is pretty much standard temperature pressure at sea level. And even at our altitude here of about 630 millimeters of mercury, because of the sigmoid nature of this curve, we're just starting to come down off the edge of the curve. So in our atmosphere around here, we're probably normally, most of us, running about, 95% saturated. But this answers the question that came up earlier. That is, if you're going to take on oxygen, if you're going to sit around and breathe oxygen, it's not going to buy you much. Because if your lungs are working normally and you're fully oxygenating the hemoglobin as those erythrocytes are moving by the alveolar space, under normal circumstances, you'll be 100% saturated. You can't really put much more oxygen on because you're right at the top of the curve. Now, it's certainly true if there's something has gone wrong and you have pneumonia and you can't, and you don't have full access to the full area of your lung, or if those diffusion pathways have gotten greater, then 104 to 106, you may be down on the curve. So what you do is you push the oxygen levels up therapeutically to try to raise these oxygen concentrations, but that's under pathologic conditions. So, any questions up to there? Well, let me show you a couple slides then. Now, this first slide is just a formalization. It's a more accurate drawing of what I put on the board. And this is simply describing the relationship between the partial pressure of oxygen and the percent saturation, showing that by the time we get up to 100 millimeters of mercury, we're virtually fully saturated. And as we come down on this curve, we'll see that here at 40 millimeters of mercury, we're about 75% saturated. We're up such a steep part of the curve, it's easily now to go to full 100% as those erythrocytes are moving by the alveolar space. Now, what you have to picture here, and sort of in your cartoon of how this works, is you can imagine those oxygen molecules binding to the iron on hemoglobin. Now, what the next step to imagine here is what makes them more likely to bind or less likely to bind. So let's now imagine a situation where, I hope I have this slide right, let's imagine a situation of temperature. So let's imagine a situation where the blood is warmer. So you can imagine this out in the tissues. We were exercising and the blood moving through the muscles is a little bit warmer. So what we're going to see here is a rightward shift. So if you walk through these curves, and it takes some practice to do this, if you walk through these curves, you find a rightward shift is telling us that for a given partial pressure, you have a lower saturation. So this rightward shift is telling you that the hemoglobin is more likely to relinquish its oxygen. To me, with temperature, that's most easily understood. You can imagine those iron atoms vibrating at a particular temperature, and as you raise the temperature, those iron atoms are vibrating more vigorously. They're more likely to shed the oxygen. So to me, it's fairly easy to think intuitively about increases in temperature and lower affinity. By the same token, you can think about cooling the blood because there's less vibrational energy in those iron atoms. They're more likely to hold on to the oxygen, so the oxygen dissociation curves move to the left. So what I'll ask you to do here this weekend is spend a little time with these oxygen dissociation curves. It takes a little bit of practice to look at them, and then we'll come back on Monday and we'll talk about something called the Bohr effect, where we'll shift those curves to the right with lower pH.